Hello, my name is Andy Schweitzer, and this is a little video that says, when I neutralize, am I always neutral? It's tagged off of a short video, one on what is a salt, and the other one is when I have a salt, what is the pH of it? So when you neutralize something, I'm going to use the same example I had in the previous video. HF plus H2O yields F negative plus H3O plus. And let's just say initially I have a 0.1 molar solution, and say it's 0.1 moles per liter, and it's in a 1 liter solution. So I have a 0.1 moles involved. And I'm going to start with this mole here first. So when I neutralize this thing, okay, my equation generally a neutralization reaction would be an acid plus a base would yield a salt and water. Okay, so in this case it's going to be, for this it would be HF plus, I'm going to use NaOH as my base. NaOH would yield NaF and H2O. You should note that this is a weak acid and this is a weak base due to the F right here. Now this is the way you might want to write it, but it's not as useful for us doing some calculations. In the nuts and bolts of what's happening here, when I drop an HF in here, it ionizes to form H plus ions. The H plus ion then attacks the F well, the HF is here. I'm actually going to drop in the NaOH, and the NaOH will have a hydroxide which attacks the H plus ion, producing water. This thing then removes this, and Le Chatelier's principle says, okay, it rolls over. Every time I remove one of these, I lose an HF and I gain an F negative. Another way of saying that might be similar to this would be HF plus OH negative yields F negative plus H2O. Alright, so every time I add hydroxide, I lose one of these guys and I gain one of these guys. This is a pretty common scenario if you're doing a titration. Give myself a little more room here. And again, on titration, I would simply have a burette, okay, and I would be dropping in, if I have HF here, I would be dropping in my base, neutralizing as I go. The question is, am I always neutral when I am neutralizing? And the answer is no. Here's an example, okay? Very common for a titration is to titrate to the equivalency point, which means I will add, in this case, if I'm adding hydroxide to this particular reaction, and whenever we do it with this, I'm going to do a little bit of stoichiometry first, and then I will do my ice table afterwards. Okay, so stoic first, then your equilibrium. So I'm going to add to my equivalency point, I'm going to add 0.1 moles of hydroxide ions in the form of NaOH, and it's going to be a solid. I'm just saying that at this point it's a solid. I don't want to increase my volume at all because that adds one more calculation on. But either way, that means I'm going to lose 0.1 moles of this guy down to 0, and I had none to begin with, but I'm going to add 0.1 moles of this guy to 0.1. So now all I have left at my equivalency point is a weak base. So in this case, if I titrate to my equivalency point, I'll actually be basic. Okay. Now, at this point, let's go ahead and calculate. I can't actually use this equation any longer because I don't have any more acid. I'm going to flip the equation around and use the base version. F negative plus H2O will yield HF plus OH negative, initial stoic ratio, and ending. I have a 0.1 moles still in 1 liter. This is the part that would change if I'm adding volumes together, and that's the only part. I would still have my same moles. I'll just need to divide by the newer, larger volume to get my new molarity. In this case, I have to stay at 0.1. Not playing a role. 0, 0, minus x plus x plus x, 0.1 minus x, x, and x. plug this into your Kb expression, which is the concentration of HF over the concentration of hydroxide and F negative. Solve for the hydroxide concentration, which is X, and you get a pH that is around 8.08. I did this on a previous video. Alright, so in this case, at my equivalency point, all of my acid is gone, and all I have left is a base, so I am actually basic at my equivalency point. I'm not neutral. If I were tracking this on a pH meter, I would see it look like this. This would be moles of hydroxide added, and let's just say this is 0.1 moles. And let's go pH on this side. I would start out being acidic, and it's a weak acid, so let's just say this is 7. I'd be taking it right around here. And as I add my moles, you'd see it slowly, it's buffering, in a buffering zone here. And all of a sudden, as I start, my HF starts to dwindle, I would see a spike right here. And it would look like this. This, right where it spikes, is my equivalency point, which should be 0.1. Therefore, the equivalency point occurs right around pH of 9. Okay. I could also do what's called a half equivalency point. And the half equivalency point is very common. This means I have added half of my moles. So let's go HF plus H2O yields H3O plus F negative. Again, I have 0.1 moles of it in a 1 liter solution. All right, and I'm going to add, in this case, a little stoichiometry. I'm going to add 0.05 moles of NaOH. This will cause me to lose 0.05 of this down to 0.05 moles, and I'll have none to begin with plus 0.05 moles. Now I took the half equivalency point. It doesn't matter where you take. You could, whatever you add to this thing, you just got to subtract and add. At this point, I would divide by my new volume if I had a new volume. In this case, it's 1 liter. I still have some of my acid. I still have some of my base. By definition, anytime you have an acid and its conjugate base present in the same solution, you are a buffer. Okay? Anytime you have both of those taking place, when you chart this out, like I had before, in fact, I'm just going to use the same drawing above here. I'm only going to titrate to here, halfway. So this thing is buffering in this zone. As long as I have both of these present, it's going to hold a certain range of pH. That's what we call it, a buffer. Alright, so now I have my concentrations of each. Just go initial, stoichiometric ratio, ending, 0.05, 0.05. Now, they are both the same concentration. I should note, with equal concentrations, the larger K value will determine the pH, or its acidity. So the acid is a significantly more larger strength than the F negative because of the Ka values. That was covered in the previous video. The Ka value for this guy is 6.6 e to the negative 4th. This guy's is 1.51 e to the negative 11th. They tag off each other via the equation Kw equals Ka times Kb. Right? So much stronger, so this guy will win. Now, in this case, water's not playing a role. I don't have any of the H plus to begin with. Minus x plus x plus x is to be 0.05 minus x, x and 0.05 plus x. I would plug it into this hydrolysis equation, even though it really doesn't matter. I'm going to put it right here. It doesn't matter if you use the acid or the base version. I'm using the acid equation, so I can use the acid Ka. The Ka equals 6.6 e to the negative 4th. The concentration of the H3O plus, concentration of the F negative over the concentration of HF. Now you'll notice mathematically at this point we get x. I'll use the shortcut rule right here to avoid a quadratic equation. This is 0.05 and 0.05. Anytime you have equal concentrations, this is important. They cancel, and the x value equals the Ka. This is 6.6 e to the negative fourth. If, in that case, if I take the negative log, get towards the bottom here, of this value, at this point, I get the pH. All right, 6.6. Equals 3.18. So my pH equals 3.18, and that is my constant. That is my pH at the half equivalence point. I've now done the pH here, and I've done the pH like right here. Okay. You could do it at any point along the way. I'll also mention just quickly that if you take your negative log of your Ka, it's called the pKa. And at that point, if your concentrations are equal, your pH equals your pKa, and your H plus ion concentration equals, I should say your pH equals your pKa, and your actual H plus ion concentration equals Ka. So a little bit of a shortcut there, some we'll talk about in a future video. Thank you.